with the idea of parameter estimation and fitting. So my work, mostly I've been thinking about the immune response and treatment, and then virtual clinical trials, and optimizing delivery of treatment, etc. And when you start thinking about digital twins and virtual clinical trials, then parameterization becomes increasingly important, because you really need to estimate the posterior distributions for our patients to be sampled from. So this was our foray into digging a little bit deeper into how do we best estimate the posteriors to generate our virtual patients, and what do you do when we don't have all of the data. So let me see if this works. Okay, so first I have to say the people who did the work. So this project started with two undergrads, Jamie and Daniel. And then I attracted a very good physicist at our university, TMU, which is a 20-minute walk that way, Kathleen, who is currently at the ITEMS Center in Riken in Japan, where she was working with Donald Warren, and her student was Christian Quiroet. So all of us together worked on this project, and it's just recently been published. So we're going to consider 5 increasingly more complex mathematical models for tumor growth. We have some experimental data. We'll use Markov chain Monte Carlo or Bayesian inference to estimate the parameters. And we're going to look specifically at how the number of parameters that you're trying to fit affect your results, how the prior that you assume in Bayesian inference affect your results, and how to properly handle missing data points. So we're going to start with the most complex model first. So this is what we call the Richardson's curve. This is generalized logistic growth, but here we have the minimum of alpha, which is this parameter here, or 1. And I'll show you a bit why we use Richardson's curve, because it's a little bit more nicely behaved than regular generalized logistic. Of course, then we look at the simplifications of all of these models. So when you set alpha equals 1, you get regular logistic growth. As alpha goes to 0, you get Gompertz growth. As alpha goes to infinity, you get exponential growth, but it's capped. So we call that X cap. It's capped at the carrying capacity. And then if you throw away the carrying capacity, you get regular exponential growth. So those are our 5 models, from the most simplest, exponential, moving up towards Richardson's curve, which is generalized logistic. This is our data set. So these are all the different colors are different mice. There was 10 C57 black 6 mice that were injected with Lewis lung carcinoma cells, 1 million of them. And then, they watched the tumors grow and started measuring them when they were measurable, and then had to sacrifice the mice when they reached 1,500 milliliters cubed. What's interesting here, there's 2 things that is interesting. One is that, of course, not all the tumors are visible starting on the same day. So, on the first day, I think only 2 mice tumors are visible. And then the next day you get more and more and more, until later on when all the mice have visible and measurable tumors, and then they die off sort of one at a time as well. So we have an incomplete set of data here and an incomplete set of data there that we'll be dealing with. And the second interesting thing is that this data set actually is more like, a multiplicative error model rather than an additive error model. So everything we do then is going to be plotted on the log scale, because the log of the data set then has a constant standard deviation. We're going to take the log of the data. So for Bayesian inference, you use Bayes' theorem, which basically is this. It says your posterior for your parameter set given the data is the likelihood of your data given your parameters times the prior of your parameters divided by this normalization, which is like the information of your data. This is hard to get, so we throw that all away. It's going to be constant anyways for all the things, and we'll just look at the differences. And this piece here, so the likelihood of the data given the prior that we assume. Okay, so what do we set for the likelihood function? That's the exponential of the negative of your sum of squared residuals. But how do we calculate the sum of the squared residuals when we have 10 mice? And what we did is we summed over all the mice and sum over all the data points for those mice. So this is sort of fitting all the data at once, considering each individual mouse rather than fitting to the average of all of the mice. This is similar to, no, it's not similar to, it is exactly equal to sequential Bayesian updating, which is a machine learning technique, if you're familiar with. But basically, it's equivalent to if you were to fit to one mouse, assume whatever prior you want to fit to one mouse, then use that posterior as input prior, fit to the second mice, and you do that sequentially 10 times. Then what you get out as a posterior is equivalent to fitting all of them at the same time. Okay. Right. Yeah, I already mentioned this, that we're going to be working with this sort of log normal distribution. And then because the standard deviation is constant. Okay, so just some nomenclature, because I know not everybody's familiar with Bayesian inference. So once you do MCMC or Bayesian inference or ABC or whatever you want to do, you're going to end up with a posterior distribution, a joint posterior distribution. So then how do you get the parameter? You know, usually we just want to take one set of parameters and go ahead and move on with our lives and do what we wanted to do in the first place, right? So what set of parameters do you pick, right? So you can pick the best fit parameter set, which is the one that maximizes your likelihood. So it's called the maximum likelihood estimate. You can pick the most likely set of parameters, which is like the mode of your joint posterior. So that's the MAP, maximum a posteriori estimate, right? So those are the two sort of most common choices that you would make if you wanted to just take one set and continue on with your life. And we're also going to be looking at profile log likelihood curves, which is similar to what Hector was showing, I think, in his Bayesian field something, I forget what it was called, where we're going to look at the shape of these log likelihood curves as you fix one parameter and then fit all the rest as a way to measure sort of the confidence you have, or the parameter identifiability is what we would say here. So this is the result of fitting the first, fitting the model as I showed it to you so far. So this is the exponential model, Gompertz, logistic, XCAP, and Richard's model here. This is the most complex. Basically, the data are all the dots, and then we see the maximum likelihood estimate, the best fit, and then the 68 and 95 confidence intervals are the shaded regions, which maybe you can not see. This is very tight. This one is the Richardson's more complex, so we have more uncertainty here, especially in the lower regions and the upper regions. Here's all the models plotted together, so using the maximum likelihood parameter values on the log and linear axes, and these are the profile likelihood curves. So this shows, so this one is for the initial condition. So you would fix the initial condition, then fit all the other parameters and measure, you know, calculate the maximum likelihood or log likelihood that you could find. And what's interesting is that the shape of these curves, one, tells you how identifiable your parameter is given the data that you have. So here, you know, these shapes are very identifiable. So for example, the purple curve here, this is the exponential model. This is very identifiable. So the data is sufficient enough for us to estimate what the initial condition is for the model, right? But the estimate is really bad, because this is telling us that the initial condition for the exponential model is around 20, when we know that we injected 1 million cells, which is like one millimeter cubed, right? So the estimate is really off. So this was for the growth rate, carrying capacity, and alpha, the parameter in the generalized logistic growth. So this one is not identifiable at all from the shape of profile likelihood curve. These ones are not, this is carrying capacity. They're not identifiable. Also, well, you can see that from the data. We have no indication of where the leveling off is, right? And the other thing that's interesting here is that the Richardson's curve, which again, I showed you sort of runs between Gompertz when alpha is near 0, logistic when alpha is 1, and X cap when alpha goes to infinity. The orange line sort of hugs those curves as you move across. So the orange curve hugs Gompertz when alpha is, well, this is for the growth rate, but you can see it in all three of these. It hugs one, and then it jumps to the next, and then it tends to follow the other one. Okay, so that would be, sufficient to move on with your life if you wanted to, but we were not satisfied. We wanted to dig deeper into what are the effects of the assumptions that we have made here. 1 in the model form, 2 in the throwing away information on the data, and 3 in the choice of the prior. So this slide just shows the different perturbations that you could have in Richardson's curve and why we chose the particular one, which had the growth rate mu divided by the min of alpha and 1. That curve is shown in orange. There's different variations, one where the denominator is just mu over alpha, or just mu, that's green, and blue is mu over alpha. So this is the most interesting piece. Generally, they all kind of behave the same when we look at the different model parameters. But when we vary, this is we're varying alpha. So you can see in this particular one that the other variations of generalized logistic growth perform very badly when you start changing alpha, namely they blow up. And we sort of chose the orange one, which fits the nice behavior of both and doesn't have the blow up problem. Okay, this was parameter sensitivity. This is using a local method where you look at central differences. The only interesting thing here, I think, is that, where is it? This is initial conditions. It's sensitive early on, and then most of the models become unsensitive later on, except for the exponential model. The growth rate sensitivity is high for later times for the exponential model versus the X cap, of course, because you've thrown away everything once you hit the cap, etc. So getting to more interesting questions. I mentioned that we have unmeasurable data, right? We know that the mice were injected with cells, 1 million cells. We know that it will grow into a tumor, but it's not yet measurable, right? So in the first likelihood function, we just threw away the information because we didn't have a measurement. But now we're going to account for the fact that we know it's there, it's just too small to measure, right? So we are going to change the likelihood function to be the product of the likelihood of the measured data times the product of the times the likelihood of unmeasurable data. So what is that likelihood for unmeasurable data? This one is the same as before, but we need to create a new piece here, the likelihood for unmeasurable data. And basically it is the probability that you have a mouse that at that time has a tumor that is below the lower limit of detection, plus the probability that you have a mouse that at that time, TK, has a tumor that is above the upper limit of detection, right? So once it hits 1500 millimeters cubed, the mouse was sacrificed, but we know that it would have been big if the mouse had been allowed to live. Then you add those things up and you raise it to the number of mice that had unmeasurable data. So if you have no unmeasurable data points, then U is 0, this whole thing is 1, and we're left with the likelihood as before. So if we use this, I guess I should mention, the lower limit of detection we're assuming is just below the smallest measurable tumor, which was 19 millimeters cubed, and the upper limit of detection we set at 1500 because that's the ethical limit. Okay, so if we use this new likelihood function in the MCMC algorithm, It modifies the results a little bit. Basically, we now have lower predictions, smaller predicted tumor sizes at early times, and larger predicted tumors at later times. Okay, so the dotted lines are the old method where we didn't account for unmeasurable data, the dotted lines here and here, and our new predictions are accounting for the fact that we couldn't measure it. And we know it's there, it's just too small, right? So I think everybody can agree these are better fits because we know that they're there, we just can't measure them. And then what about the choice of the prior? So normally, it's very, very common to assume a linear uniform prior in Bayesian inference, but it doesn't always give the best results. And I can't say that one is better than the other, but I will say that you should try other priors because it does affect the results. So here we considered a log uniform prior and compared it with the linear uniform prior, which is what was done before. And these are the bounds we worked with, which are large enough that they are very inclusive and very generous. And this is the results. So this is a bit of a busy slide, but basically each sort of colored row, this runs from Richard's model, XCAP, logistic Gompertz, and exponential at the bottom. Okay. The top line is when we include unmeasurable the data and we use the log uniform prior. So I would argue it's the best estimate that we can make of the posterior. The line just below it is with a linear uniform prior, but also including the unmeasurable data. The third line is excluding unmeasurable data and using a log uniform prior. And then the bottom one is excluding unmeasurable data and using a linear uniform prior. And so what we see is that sometimes it makes a really big difference and sometimes it doesn't. So, so for example, here, this is the exponential model. I showed you before the exponential model was fairly well constrained. So the difference between these two is, which is using a linear uniform or a log uniform prior, is very minimal, right? There's basically no difference for exponential model. But the difference between including unmeasurable data here versus ignoring the unmeasurable data is big, right? These are they're statistically different. So that's for the simplest model. In the most complex model, it makes a big difference. So for example, here, well, what's a good example? Up here. So this is estimating the initial condition for the Richardson's curve. So when we include the unmeasurable data and use a log uniform prior, I forgot to mention the dot in the circle and the star. The star is the most likely parameter set from the joint posterior. Okay, so that's the star. And the circle is the marginal posterior's mode. So there's different ways of estimating what the value should be. They're close when we do all the things I said we should do, include unmeasurable data and use a log uniform prior. They're very far apart when you don't do those two things. And they're very statistically different estimates. This is on the order of 10 here. If we look down here to try to estimate alpha or carrying capacity, they can also be very different, right? So this could be, 2 orders of magnitude difference in the estimate that you're getting for the carrying capacity based on those assumptions that you made in your Bayesian inference that you potentially didn't think about and just moved on with. Okay, so these things affect our estimates quite a lot when our models are more complex. The other thing that I wanted to mention is that reporting confidence intervals, as we did here, so this was like, your mean and your confidence interval or whatever you sort of normally would do, can be very misleading for more complex models, because if you don't actually look at the marginal posteriors that you're getting, you can get things like this one here, which is multimodal, right? So we have a bump here and a bump here in the blue curve. We have 2 bumps here in the blue curve. There's 2 bumps here in the blue curve. There's 2 bumps here in the blue curve, etc. Those blue curves are with unmeasurable data and linear uniform prior. So the most basic, most vanilla case of Bayesian inference is giving us multimodal posteriors that then when you report a 95% confidence interval might not make sense. So visualizing it as well is a good way to make sure that you're choosing the best estimate that you want when you move forward with the rest of your modeling fun. Yeah, so then I'm just going to wrap up. So I hope that I've convinced you that priors are important, that we should use the ones that are most appropriate for the data that we have, and we should try to include all of the known physical information that we have. Log uniform priors may be better than linear uniform priors, although linear uniform priors are, again, the most common sort of I don't know anything kind of assumption. But a linear uniform prior can make a lot of sense. It says a linear uniform prior, says that it's equally likely to be found in this range from 10,000 to 20,000, then from 1,000 to 2,000, whereas a log uniform prior assumes that it's equally likely that it's 10 times more likely to be found here than in here, whereas a log uniform prior assumes that they're equally likely. And for some of the parameter values that we're trying to estimate and we don't know where they lie, this assumption may be a better fit. So I think we want to consider these assumptions that we make, log uniform versus linear uniform. We should, I would argue, always be including measurements, even if we don't have the measurement, but the fact that we know the measurement was there. So accounting for these upper and lower limits of detection, it seems fairly straightforward to do, and it does affect the results that we get. And by fixing some parameter values here, I've done it a lot. We just fix something like the initial condition because we know what they injected, and then we move on. But we're introducing a lot of bias when we do that. Although then when we try to estimate the initial condition, as I showed you with the exponential model, we could be off by 20 orders of magnitude, off by a factor of 20. Right, so these decisions that we make affect our results significantly. So we've proposed this framework here for using Bayes' theorem to account for the unmeasurable data and choosing the priors appropriately, and using the profile likelihood curves to check for identifiability and sort of the confidence that you have in your estimates when you then move forward to do whatever fun thing you wanted to do, like generate your virtual clinical trial, etc. And I'm just going to say thank you very much to the organizers for the invitation to talk, to the fields, to funders like NSERC, and to everybody here for listening. So thank you.